course. So another example which is special. Okay, determine a QH, which is shorthand to find a difference, for V of x times, let's use an f prime of x, and then taking another derivative. And using only fx minus h, fx, and f at x plus h. So it's going to be a central difference. And you may assume v of x is known. So it's a known function. Whatever x you have, you can put it in. Okay, so one thing we could do, is doing a shitload of Taylor expansions and see what has to drop out and stuff like that. Well, in this case, we're going to do a very simple other step, is we're going to repeat central differences. So we do this using repeated central differences. So let's see what happens. So I'm going to write down v of x times f prime of x, and then take another prime. And that's approximated using a simple central difference, and then 4 first derivatives. So basically, this thingy in between, that's just some function g of x. So I'm basically looking at, so it's even equal, still equal, it's basically, I want to know g prime of x. So if I do that one, I can approximate it using, let's say it's g central, so it's g at x plus h minus g at x minus h, and then divided by h, or 2h. 2h it should be. This is just a simple step. But now I know what g is, basically this, so I can put it back in. So I get v at x plus h times f prime at x plus h, I need more space, minus v at x minus h times f prime at x minus h. And then everything is divided by 2h. So this is just the first step. So now let's take a look. I have another derivative over here. And I can change the color. I have a second derivative over here. So let's approximate those two using another central difference again. So let's scroll up a little bit. So then I can do another approximation. I can say this is approximately the vx plus h times some approximation. So let's do a central difference again, 2h. And it's central, so I need x plus h plus a step, so I get f at x plus 2h minus f, one step less, so it's x. And then I get the minus, and then I'm going to do this part. So I keep the v at x minus h, and then I have another division by 2h, and then I have f at x itself minus f at x minus 2h. So this is two central differences around x minus h. And then everything still has to be divided by 2h. But the last one is this one. Okay, so let's simplify this a little bit. So we have that v at x times f prime of x, and then taking derivative is sort of approximated by one fraction vx plus h times f at x plus 2h minus f at x minus v at x minus h times f of x minus f at x minus 2h, like this. And then I have this 2h divided by this 2h and this 2h divided by this 2h. So I can divide by 4h h squared. Okay, so we found an approximation. Is it the approximation we wanted? Does it satisfy all criteria I set at the beginning? I'll scroll up. Does it satisfy what I want? And the result is the majority says no, and that's agreed because here it says x minus 2h, and here it says x minus 2h. Okay, anyone has a suggestion how we can solve this problem? Taylor expansion. Oh, yeah, that might be true, but then I get derivatives, and I don't like derivatives in my approximations because I want to get rid of my derivative. Basically, I want to have that x plus 2h, or minus, becomes x plus or minus h. I can take, instead of steps of h, which result to this one, I can take half steps, and I get this one. So, instead of steps of h, comma, take steps of a half h in the derivation. But that basically means that everything where there's an h in this formula, I can replace it by a half h. So replacing h by a half h gives, I'm going to write the result down, v at x times f prime of x with another derivative is approximately v at x plus a half h times f at x plus h minus f of x minus v at x minus a half h times f at x minus f at x minus h divided by h squared. So this is the final result. So this is the major result of this exercise, or this example. It's also in the book. Then you might say, okay, so this part, that's an issue. But because you know the v function, that isn't an issue. You can just plug in the x and the h and you get a value. So you do know it. Similar way, this is not an issue. This is a nice formula. It's in the book. I know it from the top of my head. I recommend you know it too, because it might be useful in the future if you don't have to look up everything in the book. Okay, so quick recap. For this formula, we can use this one. And I didn't prove it, but it is second order accurate. You can prove it using a shitload of Taylor expansions and a lot of manipulation. If you do, you will find order h squared exactly.